You'll recall from our work in the visual calculus series that there were two topics that we focused our attention on. One was the concept of signed area, and the other was the notion of the slope. And we've now covered how to deal with approximating numerically the signed area of an arbitrary curve, and so that leads naturally to whether we can also ask the question, what is the slope of an arbitrary curve? Remember that we started off in visual calculus working with very simple shapes, like this rectangle. Clearly the slope here is 0. And then we expanded to more complicated shapes. But in every case, the slope at any particular point was clear. It was simply that the curve was made up of multiple straight lines, each of which had a well-defined slope. But when we move to an arbitrary curve, we have to rethink this question. What is the slope of a curve? Well, there are, by definition, no straight line segments in it. So what does it mean to even talk about the slope? And yet, if you think about it, suppose this were a position versus time curve, such as we had in the trip to my grandmother's house. Well, what did the slope represent in those various approximations we used? The slope was clearly identified with the velocity. And so you ask yourself, if this is the shape of my position as a function of time, surely the car had a velocity at every particular moment in time. And so the fact that the car has a very clearly defined velocity at every point in time suggests that this curve must have a clearly defined slope at every point in time. And that's really our quarry. That's what we're hunting for. So we're going to go back to the same curve that we used to think about this for the signed area under the curve, this y equals x squared curve. And let's think about how we would find the slope right here at the point 3, 9. Well, one obvious thing we could do is we could start here at the origin and say, when I go from the origin to 3, 9, what is the slope? Well, we know how to find the slope between 2 points. y2 minus y1 over x2 minus x1. We've been doing it since Algebra 1, if not sooner. And that's going to tell us that the answer is 9 minus 0 over 3 minus 0. So we have a slope of 3. But that's the slope from here to here, and that line kind of looks like this. That doesn't quite seem to do it for what we mean by the slope of the curve right here at 3. It visually seems like it's quite a bit steeper at that point. In fact, that notion of it being steeper is related to the idea of a tangent line. After all, we can definitely draw a line that is tangent to a curve. We've drawn lines that were tangent to circles in geometry. We can draw a line that is tangent to the curve, meaning that it only touches right here, and it's a little ways away from the curve at all other points. And it's realistic to ask, what's the slope of this line? Maybe the slope of the tangent line is what we mean by the slope of the curve. It's another reason to believe that we ought to be able to find the slope of a curve at an arbitrary point. We'll just put this in, this tangent line. But it still doesn't tell us how to construct such a tangent line or to how to find the slope of that line. So what else can we do? Well, if you think about it for a while, one idea that comes to mind is, what if we found the slope between a point that was closer to 3 and 3? For example, this point here at 2, 4. What's the slope of this line? Well, what do we get? At x equals 2, we have y2 minus y1. That's going to be 9 minus 4 over 3 minus 2. That's going to give us a slope of 5. And similarly, there's no reason that we should prefer the 2 as a number below the point we're interested in over a number like 4 that's above the point we're interested in. What about the slope from here, from 4 to 16? I'm sorry, from 4 comma 16 down to 3 comma 9. What if we apply the y2 minus y1 over x2 minus x1 to that? Well, let's see, at x equals 2, at x equals 4 rather, we're going to get 16 minus 9 over 4 minus 3. That's going to give us a slope of 7. Well, that's sort of interesting. At least the slopes here to these curves look a little closer to what the slope of the tangent line is. So how would we get a better approximation? How would we get closer to the number that we're looking for? Well, my guess is you're pretty quick to realize that we could go even closer. What if we went in here at 2.9? Or what if we went in here at 3.1? What would we get? Well, let's make a little table. Just see if we can't approach this more systematically. So let's see, when we chose 0, when we chose the origin, we came up with a slope of 3. When we chose 2, we came up with a slope of 5. I'm going to leave some space here because of what I've suggested, but when we chose the point 4, we came up with a slope of 7. Now, what about if we choose 2.9? Or, as I mentioned, what if we choose 3.1? Well, with 2.9, you get a slope of 5.9 for that tiny line that connects you from right about there to there. If you choose 3.1, you get a slope of 6.1. Well, you can see where this is headed. I'm going to try a point even closer. What if I tried 3.01? Or, on the other hand, what if I tried 2.99? I'd get, well, what would I get? Well, here I'm going to get 6.01. Again, I'm not doing this calculation, but it's easy for you to verify it. And I would encourage you to do it, even though you know how to find the slope between 2 points, just to make sure you really understand how we're applying it to this situation. Here we get 5.99. Well, what's the point? It seems that we are getting closer, both from above and below, to one particular value. Something right around 6. And in fact, if you continued to do this with increasingly closer and closer points, just a tiny bit away from 3, both below and above on the x-axis, you would in fact get numbers that continue to get closer and closer to 6. The problem, of course, is what happens if you put in 3? Well, then you're finding the slope not between 2 points, but the slope of a point. And that gives your calculator an error. It looks like 0 divided by 0 on paper. And so it's hard to say what's going on there. And yet, there is this strong sense that we are converging to a particular value. Well, obviously, to gain any real confidence in what we're doing, we'd have to look at a variety of curves and so forth and see that this approach held up in a number of circumstances, but in fact, it does hold up quite well. And so we seem to be onto something here of using closer and closer approximations to get closer and closer to the idea of the slope of a curve at a particular point. See if we can't sum up. So initially it does seem a little bit puzzling to talk about the slope of a curve because there are no straight lines. But we argued first that in a d versus t graph, the slope would represent the velocity, and it's obvious in the real world, if you will, that if you're driving a car along a path that gives you a particular d versus t curve, you must be going at some velocity at every point. And similarly, we argued in a visual way that the tangent line has a slope. And even though it's not clear how to construct such a tangent line, we're persuaded that one exists. And so maybe the slope of the curve is really synonymous with the slope of the tangent line at that point. Well, these sounded like good ideas. The real thing that increases our confidence is that when we actually test out, both in the example I've given as well as numerous other examples that we haven't gone into, when we actually test out the idea of using points closer and closer to the point in question, we seem to get closer and closer to a particular result. The results seem to converge to one number. And so we're going to take it based on that experimental evidence, if you will, that we can get a pretty good numerical approximation to the slope of a curve at any particular point simply by using this method. Again, I encourage you to teach these concepts, particularly the ones here in the summary, to someone else to see if it has really cemented in your own mind. The best way to learn is to try to teach it and then have someone ask you a question.